Okay. So we're going to do 2.5, finding the zeros of the polynomial. And it's really just combining 2.3, 2.4 into 2.5. I'm just going to show you this part, and then we can just kind of read through it together. So basically what we're going to do now is we're going to be given a polynomial function, and we're going to either be able to factor it or, you know, start completing the square. So that's like if it was a quadratic. We could try to factor it, like if it was factoring by grouping, or maybe there was a GCF, so we could try that. And then if none of those options work, then we're going to have to do like our rational zero test, where we're doing P and Q, and then we look for a rational zero that actually results in a remainder of 0 with synthetic division, and then we'll be able to find all the zeros. So that's really our goal today, is to be able to be given any type of polynomial function and then be able to find all the zeros from it. Okay, remember what it means to either find the zeros or write it in completely factored form or find intercepts. Remember those terms and, you know, what that question is really asking you to find. Okay, so you ready to get going on it then? We're going to get right into it. So I'm trying to kind of shorten this, but I don't know that I'll be able to. So we're just going to try our best right now. Okay, so example 1, let's do this. Find all of the zeros of the polynomial. And let's say we're given f of x equals x to the 4th minus 3x cubed plus x squared plus 4. Okay, so a couple things. First of all, we've been given absolutely no hints, right? So we don't know any factors, we don't know any zeros, so like that option's out. So now we want to see, okay, what am I going to have to do next? Now, here's the thing. There's going to be two types of problems on the test. One that you're allowed to use the calculator on, and one that you're not allowed to use the calculator on. I'm going to show you both ways right now in this one example. So let's say that we weren't allowed to use the calculator. What option do we have to do now? What do we have to do next? That rational, what? Zero test, right? P and Q, remember that? Because we don't know any factors, so we have to figure out what are all the possibilities that we have going on here. So that's where we'd have to start. So like step 1, you have two options. We're going to do without a calculator first. So without a calculator, we're going to have to do the rational zero test. So we're going to have to do our P and Q. And some of you, only a few, but you mixed up P and Q. Okay, so you got to remember which one's P and which one's Q. So what do we got going on? Which one's P? The last one. Okay, so P is 4. So the factors of 4 are 1, 2, and 4. Not a big list, so that's good. Okay, and now our factors of Q are, remember that, leading coefficient, so it's just plus and minus 1. So this is like not a bad scenario for us right now, because there are only 6 possibilities, right? And we know there has to be 4 zeros. So we kind of have a good chance, right? P divided by Q then will just result in plus and minus 1, plus and minus 2, plus and minus 4. Okay, so now if you were going to go without the calculator, what is step 2? You'd have to use synthetic division to find a zero. And I think everybody knows how to do that, right? You start using synthetic division. When you get the remainder of 0, you know it works. Everybody okay on that? If we don't do that, and now I'm going to move into the calculator because we haven't seen that one yet. Okay, so this is without a calculator. Now let's run the same scenario with a calculator. This is still step 1. Okay, so now step 1, if you have the use of the calculator and it doesn't say like find the zeros without it, then what you're going to do is you're going to put the function into the calculator. So if you have a calculator today, go ahead and get it out. Okay, so we put our function in. So x to the 4th minus 3x cubed plus x squared, and then plus 4. Okay, and now we're going to graph it. And what we're going to do is we're going to find the 0 in the calculator. So the calculator will show us the real zeros, right? Anything that shows up on the calculator, on the graph, means that it's a real 0. What do you notice about this graph? Only has 1 0. Where's it at? It looks like it's at 2. I'm going to verify that. Okay, so there's 2 ways to verify it. You can go to the table if you think that it's an integer value, which indeed it is. So we can see, you can't really see it on my calculator right now, but it says 2 0. Okay, so we know it's a 0. You could also go, to second trace, go to the option number 2, go to the 0, get to the left, get to the right, hit enter all that time and guess. Okay, so those are your 2 options, but everybody can see the 0 at 2. Now, what else do you notice about the 0? It's a double, and how do you know it's a double? It bounces off and it forms that parabola shape. Do you see it, how it doesn't cross through? This is really, really important to recognize this. So this is a double 0. So here's the thing. In the calculator, just sketch a little cute little graph there, okay? This is what it looked like for us. Okay? So I can see that there was a 0 at 2 0. I'm going to move this now. Okay? I'm also making myself a note, which is super important, that this is a double 0. Okay, so now let's go back and think about this. If I take a look at my function, I have to the 4th power, right? It's the 4th degree. So I know there's going to be 4 zeros. How many did I just find? 2. I found 2 because this is a double 0. It means it occurs twice. That's what that double means, right? It's really like I have x minus 2, that quantity squared in terms of factoring. That's what this represents. So that means that 0 occurs 2 times. So I know 2 out of the 4. The other thing it means is that there's 2 other zeros, but they are going to be imaginary. Okay? Because if you don't see them in the graph, which we have access to the calculator so we can see the graph, if you don't see it, it means they're not there. Okay? It's because they're imaginary. So now we got to find them. So now step 2 with the calculator is going to be the same, except now I don't have to do any guessing and checking. I already know where to start with synthetic division. So I'm still going to use synthetic division. But now I'm going to use with the zeros I found in the calculator. Yes?
What makes that a double 0?
Because it bounces off the x-axis rather than crossing through. Okay? So now I'm going to do my synthetic division, and I'm going to start with 2. Okay? So now, if you take a look at this polynomial, did you notice anything about it? Particularly right here. It's missing that term, right? There's no x term, so I need a placeholder with my synthetic division. So don't forget that. So I have 1, -3, 1, 0, and 4. If you don't put the placeholder in, it's not going to work. Now I know this is a 0, so if I don't get a remainder, I've done synthetic division wrong or I've set it up wrong. Okay, so I definitely get the 0 there, which I'm expecting to get. Okay, so now you have 2 options. You can try to factor it at this point, or you can keep going with synthetic. Because I know that this occurs 2 times, I know that I can use synthetic a second time with 2 again. Because this is really 2 zeros, x minus 2 times x minus 2, so it results in x equals 2 twice. So I can just drop this down again and do synthetic a second time. Which, this is the easier, quicker option in my opinion, rather than trying to factor it, because the smaller you get this polynomial, the easier it is to factor. Usually. Okay, so now remember, you did synthetic twice. This started at x to the 4th. The first time you did synthetic, it lost a degree, took it to x cubed. The second time you did it, it took it down 2 degrees, so it's at x squared now. So I have x squared plus x plus 1 left over. Okay, I'm hoping that it factors. Ew, no, I'm not going to do the quadratic formula. Did you not see? We're not going to do the horrible quadratic formula yet. I'm not going to do it. I'm not going to do it. So I'm at a point, I'm hoping it factors. It definitely doesn't. So I have to decide, do I want to use the quadratic formula or do I want to complete the square? I want to complete the square because it's always a good time. So that's what we're going to do. So let's do that. It's going to get messy, but we're going to be ready for it this time. Yes?
So when you're using like the calculator, are you only looking for the double zeros for this?
You're looking for any zeros that you can find. In this case, we just happen to have a double zero. It won't always be that way. I mean, some of the problems, like the problems that we did in 2.3, they only had real solutions. So when you put it in, you would see every single zero. That's why you couldn't use a zero on the calculator, because you could see them all. There's no work to do, okay? So kind of give us a hint here. The type of problem that I would ask you to use the calculator with would be one like this, where you would have both real and imaginary. So you'd have to do the process. Okay, so we're going to complete the square. So I'm going to scoot that c term over, and I'm going to think about half of b. Now I already have a coefficient of 1, so I can go right into this. So I have x squared plus x. I'm going to leave that space, and then I'm going to scoot that c over. Okay, so half of 1 is going to give me 1/2 squared. Right? Now you're squaring it, so you got to square the numerator and denominator, so this is like plus 1/4 inside. So that means I have a minus 1/4 on the outside. I already know what it factors to, that's why I write it like this. So I get x plus 1/2 squared plus 3/4. Look how easy that was, so quick. Way faster than the quadratic formula. So now we're at a point where it's time to solve. Because remember, I'm looking for 0. So I'm looking for x equals answer. I'm going to set this equal to 0, and I'm going to start solving. So I'm going to subtract over the 3/4. Now, before when we did this, I would see I had to take the square root of a negative. And so I would quit. I'd say no solution. But now we've done 2.4, right? So we know how to deal with this. And because we're looking for all of the zeros, we are also going to list the imaginary ones. These are the imaginary solutions of this graph. So we're going to take the square root of both sides. Okay? This is going to give us x plus 1/2 equals. Remember, you're still going to get a plus or minus when you're solving and you're taking the square root. This is going to result in the square root of 3 over 2 and then I, right? In order to take that square root, you have to deal with the fact that it's imaginary first. And then I'm going to bring over that 1/2. So I have x equals a negative 1/2 plus or minus the square root of 3 over 2 times I. So now let's think about all of our solutions. They ask for all of the zeros. So I got to go back. And I got to see where I started. I started with my synthetic division. So I started with that real 0 of 2. There's only one thing to list here. You don't have to list it twice. You just list it once, even though it occurs twice. So we have x equals 2 and negative 1/2 plus or minus the square root of 3 over 2 times I. Everybody okay? Do you understand the difference of what you'd have to do if you had a calculator versus if you didn't have a calculator? If the problem said, you know, find some, or if it's maybe gave you a hint, or if it said do the rational zero test first, depending on what the directions are kind of guiding you to do, you would have to do one of these. It's going to result in the same answers, okay? So is it okay if I skip the second example that required us to do the rational zero test? It's the same thing. Okay. All right, well, let's keep going then. Now we're going to talk about a pretty cool idea, I think, which is conjugate pairs. Okay, so conjugate pairs is we know what a conjugate pair is, right? We talked about that before, like you take those same first and last terms and then you change the middle sign, right? So you know what a conjugate pair is. If f of x is a polynomial with real coefficients, then complex roots always occur in conjugate pairs. Okay, so like for example, if 2 plus 4i is a 0, then you know 2 minus 4i has to be a 0. Think about that idea for a second. Think about why that's true. Like, how do you get something with an I in it? Yeah, and when you take the square root of something and you're solving, what do you always have to get in front of that square root? Plus or minus. So doesn't it make sense that you'd have to get a plus and you'd have to get a minus of the same thing? Right? So it's like when you take the square root, you're solving, you have to get those two results. That's why this always has to occur in conjugate pairs, because that's the only way to get an I is to take the square root. Okay? Alright, so now you have to remember that idea, because you know I'm going to try to see how it's applied, right? So I'm going to try to do a little trickery here. Alright, so here, let's call this example 2, I guess. Let's do this. Write the equation of the polynomial with real coefficients given x equals 2 and 2 minus 3i. Okay, so we're given some zeros. We want to write the polynomial function, which means we got to take it back to here, right? F of x equals, have it in standard form, descending order, so we're going to have to multiply stuff out, right? Remember, this is where we were backing into answers, right? So it's like if x equals 2, then isn't this factor x minus 2? Okay, so I know I have to start with something like that. So f of x, I know I have an x minus 2. Now, we've been given 2 minus 3i. So let's think about that. If x equaled 2 minus 3i, then the factor would have to look like, if I backed into it, so I'm trying to set this back equal to 0, it would have to look like x minus 2 plus 3i, wouldn't it? Okay, so I'm going to write that next. X minus 2 plus 3i. Yes?
Wait, is the inverse for the I the same? Like, is that an x2, like 2 plus 3i?
Okay, so that's where I'm going to go with this next, right? So you'll notice there's only 2 zeros listed, but one of them has an I in it. If one of them has an I, then we're missing its conjugate pair. So I might not give you all of them. Thank you. I might not give you all of them. I expect you to be able to recognize that the conjugate pair is missing. So you have to fill in the blank there. You have to realize that there's a 0 missing, and it's 2 plus 3i. It's the conjugate pair to this. Do you understand that idea? Okay, so now I'm going to back into this the same way too. I'm going to take x and I'm going to set it equal to 2 plus 3i, and then I'm going to move all that over, giving me x minus 2 minus 3i as a 0. So now I have to add that factor in here. So x minus 2 minus 3i. Okay, so that's like where the trick's going to come in. I'm not going to necessarily give you all of the zeros. If you see one with an I, you need to remember you're missing the conjugate pair, and you need to add that in as well. Okay? Okay, we did a problem like this before where we were multiplying all of this out. It has some square roots in it. I hope you remember it a little bit. And remember I told you there was a quick way to do it and there was slower way to do it. So an option for us is to distribute these three terms to these three terms. Okay, it's going to take a while. It's messy. It's not so much fun. But do you see that this x minus 2 and this x minus 2 can get grouped together? And then what happens is you have the same first and last term, and they have opposite signs. So a difference of perfect squares is created here. Those middle terms will cancel, which makes this so much quicker and easier to deal with. So I'm going to show you that. The first thing I'm going to do is I'm going to ignore this x minus 2. So I'm going to have f of x equals x minus 2, and I'm going to save that for later. I have to distribute that later. It's easier to distribute these two first because I can group them like this. So when I do x minus 2 times x minus 2, I get x minus 2 squared. Now, I'm going to have x minus 2 times a negative 3i, and then I'm going to have a positive 3i times x minus 2. So I have a positive and a negative factor that are the same. They cancel. I'm left with positive 3i times negative 3i, giving me a minus 9i squared. Your other option is to take x, distribute it through. Take negative 2, distribute it through. Take positive 3i, distribute it through. So if you can't see the grouping, it's okay. This problem is just going to be a little bit longer to solve. That's all. Okay? So now I'm going to work with this piece. I'm still ignoring that f of x equals x minus 2. I'm still saving that piece for later. Okay? So now think about x minus 2 squared. Remember, you have to FOIL that out. It's two binomials being multiplied together. So x minus 2 times x minus 2 is going to give me x squared minus 4x plus 4. This minus 9i squared, what's I squared? Negative 1. So this is really like a plus 9 right here. Okay, I'm still working inside that set, so I'm still going to have my x minus 2 still waiting. I have x squared minus 4x plus 13 left over. Okay, so I still have to distribute. My only option here is to distribute x throughout and negative 2 throughout. So I'm going to have to do that next. So I get x cubed minus 4x squared plus 13x. And now I'll distribute the negative 2. So minus 2x squared plus 8x minus 26. My last step is just to combine like terms and make sure that it's in standard form. So x cubed minus 6x squared plus 21x minus 26. You got that? Okay, so you got to remember if you have, okay, let me say this. What if I gave you like a 4i? What's the conjugate pair of 4i? Negative 4i, right? If it's like a zero's in the front there, it'd be like 0 plus 4i. So you'd still have the same first term as 0. So that one can sometimes get confusing. But remember, if you're given one I term, you have to find the conjugate pair before you can get started on this. The quickest and easiest way to do it is to group this together and create the difference of squares. But if you can't, then just distribute the whole thing through. We're almost done. We're having so much fun. We got to talk about some wording. Okay, so in the book, they're going to give you sets of directions, and you know, I'm really big on how I want my answer, right? So I want you to be able to know what the terms mean, what does it mean to have to factor something all the way, and things like that. So that's what we're going to talk about right now. If I tell you this word, irreducible, so if you see this word, irreducible, means that polynomial can't be factored. Okay, so you're going to see that wording both in your book and you know, on the quiz or on the test. So example 3, if f of x equals x to the 4th plus 6x squared minus 27, we're going to run some different scenarios with the wording. Okay, so let's say we've been given these directions. Write as a product of factors irreducible over the rationals. Okay, so we gotta think about what those directions mean. They basically mean this: no fractions or square roots, okay, or radicals. Okay, irreducible over the rational. So we don't want any fractions or square roots in our answer. Okay, so now what we want to do is we want to try to factor this polynomial. So will it factor? It's an x to the fourth, right? So I know that it's going to have to start with x squared and x squared. 27, like 9 and 3 would probably work, right? We need a positive 9 and a minus 3. Okay, so I know this does factor. And normally, this is where it would end. Okay, so if it says write a product of factors irreducible over the rationals, that means I can't have any square roots, no fractions. Well, this will work. Okay, so this is how I would write my answer here, given this particular problem. Okay, so that's what we've done before. That's really like all the factoring you've done, right? This is how we would write our answer. We're comfortable with this one. Now, what if it said write as a product of factors irreducible over the reals? Now you want to think about what other kind of numbers does that include then? So real numbers are anything that doesn't have an I, right? So now that means that we are allowed to have fractions. We are allowed to have square roots. So can I factor this further? Yeah, you can. Think about this piece right here, x squared minus 3. We don't look at it like a difference of perfect squares, but it really is, right? Isn't that like x plus root 3 times x minus root 3? It is, right? Think about this piece right here. If I was to take x squared minus 3 and set it equal to 0, and I was to solve, I would add the 3, and then I would take the square root. So that would give me plus or minus root 3. Well, those can be written as factors, x plus root 3 times x minus root 3. So this piece, although we normally don't do this, we now can factor this further. Okay, so if you get these directions, that's where you have to take this. So x squared plus 9 times x plus root 3 times x minus root 3. Remember also that order doesn't matter here, right, because you're just multiplying. Okay, now finally, if the direction said to factor completely, that means you want to take this down so that x is to the power of 1 for each one of our terms. So I've already done that for my x squared minus 3. So I know that x plus root 3 and x minus root 3 will be two of my factors. What I haven't dealt with is this piece, this x squared plus 9. So it's a squared term, so I need to get it down to linear. So I'm going to do the same thing. I'm going to think about what if I was to take that factor and set it equal to 0 and solve. So now I'd get x squared equals negative 9. Well, before I'd say that was no solution, right? Because you can't take the square root of a negative, but I can write it as a complex solution now. So when I take the square root, I end up getting plus and minus 3i. So now when I go back to factor this completely, I need everything in terms of a linear factor. So I would have to write that as x plus 3i times x minus 3i. And this would be considered factored completely. So if I ask you to factor completely, even though it looks very strange to us, we have to take what we would normally do and take it further down to linear factors. Do you understand that? You might want to make yourself a note there. Factoring completely means we need linear factors. Any questions?